Hello, my friends. Hello, my RF and microwave uh, design associates. Good morning, good afternoon, wherever you happen to be around the world. Welcome back. This is Mohammed Nizami, Dr. Mohammed Nizami, coming to you from Jarash, Jordan, Jarash City, Jordan. Okay, so let's continue with our series on K and Ka band SATCOM low noise block dump converter or receiver. Now, as you know, this is my YouTube channel that you're watching me at right now. I hope I would appreciate if you can go in and subscribe and share some of these videos so we can get more numbers on the channel. I would appreciate it. That would encourage me to continue. We've started a session on the design, simulation, and modeling of Ka band SATCOM low noise block down converter. And this is not really applicable just to SATCOM. It could be applicable to 5G as well, the millimeter 5G. But anyway, I have so far four sessions in this series: one, two, three, and four. And of course, part three was two parts. I had to split the video because it was too long. So today we're going to continue doing the design. And if you recall from last time, we had modeled the system on the system view, as you can see here. And I have selected most of the components that that doesn't need to be designed. However, the LNA at the time was assumed to be a block that is with these specifications, namely the gain we need it to be more than 30 dB and the noise figure has to be a sub 1 dB noise figure. Okay, and the power capability of the low noise amplifier, it has to be up to like 13 dBm. Okay, so as you can see, please go ahead. If you're watching this session right now, make sure you watch the ones before because that's where we went through all the details of this. So this is a dual band right now with a common LNA that comes in and switches over to either one of these image rejection filters, which were designed and modeled both in ADS and in HFSS. Okay, and then we go down, and here's the IF section. So we went through various sessions of this. The convergent gain of this was giving, and we had the let's see the noise figure and the gain were swept as a function of frequency, incoming frequency, and this is what we got. So today we're going to zoom in on the LNA device, okay? And the LNA, of course, this is the design that I did in ADS. It's multiple sessions, which we're going to go through right now as we speak. So let's get going. Okay, so as you know, I'm a freelance designer. In fact, this very same project here is available for your company if you like to buy out this design and fabricate it. I will turn to you the fab files, all the schematics and bill of material and everything, and all you have to do is just market and sell this if you like. And I believe it has several advancements than what's in the market out there right now for the Ka-band SATCOM receiver. By the way, this front-end receiver is really applicable to both the parabolic dish LMBs and to the nowadays flat on the move satellite flat terminals that you see them coming out using phased array. Okay, so last time we said this was a design, and we verified and modeled this system in here. And the idea is to take the Ka band from 17.2 gigahertz to 21.2 gigahertz and down convert it to somewhere in the L band between 950 megahertz to 2950 megahertz. That's a total of 2 gigahertz bandwidth. Okay, so and that's where we said, okay, well, we really can do this in a common IF, which is a 2 gigahertz IF. But what we really need, because of the image issue, we can't fulfill the image rejection to fulfill the noise figure requirements of this, because this LNA is LNB is we're targeting the design that it should have less than 1.5 dB of noise figure for the front end, and a total gain of above 55 to 63, 65 dB. So we said, well, let's use dual filters and let's use dual LOs, and we just switch them basically back and forth. And we chop the band 1 to 17.2 to 19.2, which encompasses the commercial K SATCOM band. And the other one is from 19.2 to 21.2, which is really the military band. Now, one thing I forgot to mention is that we have also the transition from the rectangular waveguide to microstrip, and I designed that as well. So that we will go through in the next session. However, this needed to be designed so that we can have the S parameters at this port here. This is a 50 ohm port here that couples basically to the here, because we assume that this is a SATCOM signal in here, but we really have the source in here is really this this waveguide feed that comes from the antenna. And so we're going to have a board that attaches to here, okay, that will basically that will basically receive the signal and give you the L band on the other side. And of course, this side here is really shorted. That's a short side in here, short end side. Okay. So the frequency response of this, I will go through that next time. Basically, we cover easily, and we're targeting to get not more than 0.2, 0.3 dB of noise figure, or I meant insertion loss on this. Okay, so let's get going. Okay, so we had two bands, the low band, which was this here, and we showed that you switch to this filter and you go through, that's a low band. And we have the high band, which you switch over to this filter, and of course the LO you switch to the other LO. So we designed the image rejection filter last time on HFSS, and then today we're going to target the design of the LNA. So we're really going into the active devices. The image filters that are here, they were designed first as blocks in the system view, basically right here. So you just go in and grab this block, which you can just basically allow insertion loss, specify insertion loss, specify the order type and the Chebyshev, the topology. In this case, is Chebyshev. And then the corner frequencies of this curve, okay? And so we took that and then we designed it into ADS. And then, of course, in ADS, we got the synthesis from ADS, and then we took it over to HFSS, as you can see here, and I constructed the ground channels around the filter resonators. And in this case, of course, this is the high band, this is the low band. I still have an issue in here. As you can see here, the return loss is not so great. So there's an issue in here, which I have to still go back and resolve. The high band one is okay, it's good, okay. And so today we're going to go into the LNA. So the LNA, now you have really two choices. So we need an LNA to build an LNA, which has a total gain of 30 dB, noise figure of equal or less than 1 dB. And then the saturation power of the LNA has to not exceed 13 dBm, okay? So we had two choices in here, basically. We could go and select a one of the mimic amplifiers, okay, that are available commercially. As an example, for instance, and this is really in today's date, which is the 15th of December of 2024. This is what's available. From Curvo, for instance, we get this here, which has a gain of about 25 dB. So meaning, we can have two stages of this, but the noise figure is not so great. The noise figure in here is 1.3 dB. Of course, now realize that I'm trying to select devices that are QFN packages that we could basically, you could take a soldering iron or a heat flow plate and solder them. I'm not trying to select die packages because die packages will allow you to have lower noise figure. However, the fabrication of the LNB PCB becomes much more expensive. So this one really, something like this we can't use. We could use it as a second stage if you like, but not the first stage. Okay, another example from Maycom in here, and you can see this device in here. So, but again, the noise figure is this much, and we really can't cope with that. Mini Circuit also has another one, which is they're all of these mimic packages at K-band. They're like in the between 2 dB to 1.4 dB, 1.3 dB. Okay. So that leaves us a choice to go into discrete devices. And discrete devices, of course, the device I have selected after a thorough search and based on prior experience in this field is this device in here. It's really some people call it CE3520 K3. This is a super low noise hemp that is basically produced nowadays. Initially, when it started, it was NEC, and then it was California Eastern Laboratory, as this data sheet in here shows. And nowadays, this is really fabricated by several companies. There's one Japanese company that fabricates it. There's a Chinese company, and there's also Renaissance fabricates it. But this one here is a cute device, nice device that has, if you're operating at 20 gigahertz highest frequency, which we have 17.2 to 21.2. So it's just barely this here, which is about, I would say, as you will see shortly, it's 0.6 dB of noise figure minimum, okay, to this device. That's the embedded at the ports. And the gain could be as high as available gain is 14 dB, and we're not going to get that. We're targeting to get, we're trying to make a 30 dB device, so we're going to get 3 of those. We're going to use 3 of those in series. So we needed to operate to have a gain of only 10, okay? But we do need the noise figure to be less than 1 dB, hopefully. So we're allowing ourselves 0.4 dB of noise figure deterioration from the NF-min, basically 0.4 dB. That all goes to the input matching network of this device in here, which is feasible. Well, the 0.4 dB, of course, that goes to this, so we still have a gain margin of 0.5 dB, which we will allow it. Part of that will be basically the waveguide to microstrip transition, which we have here. And this one, we're expecting this not to exceed 0.3 dB, 0.25, something like that. So this is doable, okay? Now, of course, the bias for this is really, this is a GaAsFET device, so it's going to need negative voltage and negative voltage on the gate, and it's going to need positive voltage on the drain to source voltage. We're going to have, of course, drain to source is the same because the source is grounded on this. So it's about 10 milliamps, okay? So we're going to bias it at 10 milliamps, 2 volts on the drain, and about as you will see shortly, fractions of a volt on the gate, negative, of course. Okay, so the bias, like I said, when you look at the data sheet, they give you the bias point for this. It's the drain current versus the gate voltage, okay? Which we want to bias it at 10 milliamp drain current. And that is exactly about 0.42 volt, negative 0.4 volts on the gate to source voltage. Okay, so why 10 milliamps is because when you look at the noise figure, NF-min, it has a ball shape where the minimum is at 10 milliamps. Okay, and of course, this is really the small signal behavior at 2 volts and 10 milliamps. So you can see that it's specified between 18 gigahertz and 24 gigahertz, the noise information. Okay, but the gain information is specified all the way to 2 gigahertz, as you will see shortly. So this is a device that can operate from 2 gigahertz to 26 gigahertz, a very wide band. So that comes with the price of that. You have to stabilize it because that's a very wide band. And when you look at the stability factor on this device, it turns out that it's only unconditionally stable above 16 gigahertz, which means you have to stabilize it. So we can design it for 17 to 21 gigahertz for the Ka band LNB, but I'm almost certain, 100% certain that as soon as you power it on the bench, that it will oscillate somewhere in the L band, S band, depending on your layout. So, or if you, for instance, as soon as you take out the open input port, it will pick up and oscillate. Okay. Now the bias circuitry is really simple. Okay, it's as you can see here. This is one of my designs for Ku band. It's a similar device. It's not the same device, but it's going to be exactly the same topology. So we're going to have a gate source voltage of 0.43, and we're going to have a bias circuitry in here to isolate the DC from RF with introducing minimum interaction between DC bias circuit and the input side. Same thing on the drain side, okay? And the two sources that are on this side or on the other side, they're going to be grounded, okay? So, and of course, as you can see, I'm not really going to go deep into the LNA design from basics. You can refer back to Gonzalez's book, which I will introduce to you in a minute. That's this book here. Let me see. Oops. Okay. That's this book here. Okay. It's a nice book. Go ahead and purchase the latest if you can afford it. If you're a student and this is not for professionals who make money, you can download it. It's off the net. People scan this and it's floating everywhere. Okay, so the layout is basically going to be very similar to this. This is an earlier work that I did several years ago for somebody. Basically, here's the transistor in here, and here's the input matching, and here's the output matching, and here's the gate bias and the drain bias. And in this case, of course, on the input, I'm not going to have any capacitors. I will show you in a minute. Why I'm not going to have any capacitors? Because I can't really afford the loss of a DC decoupling cap on the input. So this transition here, because it's open, I'm going to go straight into the transistor. So this inside the waveguide, if you happen to poke with anything metal, you will short the transistor and damage it because this will have DC. I'm not going to use any capacitors on the input. Okay. So, okay, where are we? Okay. So, but basically this circuitry here, a small resistor with a cap in here, this is a stabilization at the output. I'm not going to have any stabilization at the input, as you can see, is because when we stabilize a transistor like this, we really don't touch the input side because this is a low noise amplifier, and anything at the input, any noise thermal noise you enhance, it's gonna basically get amplified and reduce your noise figure. Of course, the drain voltage and the gate voltage We come from negative voltage in here and positive voltage in here. We have a small PNP transistor in here to do the biasing, and the equations are here. It's straightforward. You can look this up. It's basically just so that you can track, basically, if the drain voltage drops, this will drop too, so or increase to make up for that. That's basics. Okay, so how are we going to design this amplifier? Well, there are two ways to design this amplifier. The first one, well, the classic way is that we need, for instance, when you go into the ADS environment, okay, basically we have two ways. We could either use nonlinear models or small signal models that are specific to a bias, like in this case in here, 10 milliamps and 2 volts. This is S parameters that are for this transistor in here, okay? And then you start, basically, the design is really straightforward. You can refer to the Gonzalez book on the techniques. So you could basically, you start out, first of all, you have to assess the S parameters and the noise parameters, and then assess the stability. Is it stable over the entire frequency of operation of the transistor, not just the band of interest, because we are designing in here, for instance, the LNA to be from 17.2 to 21.2 gigahertz, but we really have to make sure it's stabilized over the entire bandwidth from 2 gigahertz to 26 gigahertz, as I will show you shortly. So ADS gives you a whole bunch of functions that you can bring in, just like these. For instance, stability factor. You get this, and it will basically read the S parameters in here, and it will compute, for instance, the stability factor and the mu factor for over the entire frequencies. And as you can see in here, as I will show in a minute, the stability factor and the mu has to be both greater than 1, and we can see that they're only greater than 1 after 14 gigahertz, but below that, it's going to oscillate, okay? And we can look at the F-man, all of these parameters that you're going to. So that's the first step that you're going to do when you're designing a low noise amplifier. Now, that's small signal model. So meaning, really, if when you design this is only valid at these bias points in here. As soon as, if you have an interest to use other, and these are available from the manufacturers, these small signal parameters available from the manufacturer. Every transistor, they evaluate it on the bench, and they embed the measurements and give you files that have the noise and small signal parameters. But those are only valuable, those are only of interest, that usable at the bias point that you have, which is in this case, it's giving to us with 2 volts at the drain and 10 milliamps. And of course, it's not specified at the gate or source, because we know that from the data of the transistor, that to get 10 milliamps at the drain flowing, you need about 0.43 dB, volts, negative voltage on the gate. And of course, that's why when we make this, a lot of times the circuit in here, actually you end up tweaking this voltage divider in here to get accurate gate negative voltage on here on the transistor. Okay, some people use potentiometer in here to verify, to tweak it, but that's it's up to you. Now, the other option that you can do is that it's nonlinear. Use the nonlinear model. If you have the nonlinear model, then obviously you can bias it at any voltage you want and extract the S parameters right from the software. But the models, these models, you have to pay for them. Okay, and for instance, this is from Modalytics in Tampa, Florida. Dr. Dunleavy, that's my former associate. I did teach at the University of South Florida in Tampa for a year or two, as I recall, when I worked there. And Dr. Dunleavy was one of my associates in there. He's a great guy. And so you can go to him and ask him for this model in here. And I was fortunately I was not able to get even evaluation because they did not consider registering. I'm going to contact him personally to get this. So, but for right now, what I'm going to do, I'm going to use a small signal model that is available by California Eastern Laboratory. Okay. All right. So here's your device. You got your device, and of course, assuming that you have the background in designing macro amplifiers, uh, what this device needs, of course, the manufacturer, he gives you the S parameters, which we will look at in a moment. These are data like this, okay? So they get the transistor, the bias condition, and then they give you the S parameters as a function of frequency, and you can pick your particular point of operation and see what the S parameters are. And then, of course, they give you also the noise information, the frequency, the F-min, and the gamma that you need, both the magnitude and angle. And what I did in here is I highlighted the point of interest that I need my center band at, which is 20 gigahertz. 20 gigahertz, the minimum noise figure is 0.58. The gamma vector magnitude is 0.415 at an angle of minus 106 degrees. So we'll come back to this. But so as soon as you get this information, what you need to do, you need to make sure that this transistor, they tell you that we guarantee you, for instance, we guarantee you that you're going to get 0.58, excluding the, of course, the conductor losses. If you present to the transistor, okay, at the input side, this gamma here, which means your S111 has to be this, produce this reflection coefficient, okay? And of course, the output now has nothing to do with the input as far as noise figure, as you know from the Friis equation. So this one here, we can design it for maximum power transfer from the device onto the load. So we take the load, which is assumed is 50 ohm in this case. In my case, it's not really 50 ohm, but what we're going to do is we're going to go into this and we're going to find out what the input impedance of this filter here, okay, and this filter as well. So we're going to go to that extent. But on the input side, it's different. We really don't match the input side to be a conjugate of S11. We really make sure it's really gamma opt, which is what we're going to find out right now, or which from the simulation, or you just look it up right here. So all I have to do is when you design this, you can go straight to the Smith chart and put this point on the Smith chart here, 0.415 with an angle of minus 106, and get your transistor S11 and make sure you match to that, okay? Regardless of the, and the input, of course, is assumed as 50 ohm. So you transform the 50 ohm to what produces gamma opt, and that way the transistor sees gamma opt. And now these equations in here, I got them. These are basically how the ADS plots the noise figure circles and the gain circles. Okay, so you can specify them where you can. In this case, of course, here what I'm doing is I'm putting the noise figure minimum, plot a circle for that, plus 0, which is that shows me where that point is at, and then add 0.1, 0.2, and so forth, which all the way, it's an array of numbers. Same thing for the gain. Okay, the gain is the maximum gain available from the device, and we subtract from it these numbers, so to get these circles. But before we even get to that, you need to select the substrate, the PCB that you're going to lay this on. And in my case, I chose this substrate in here, Rogers 4003. And basically here are the parameters, okay? And what I did is here is I synthesized what is 50 ohm with a quarter wavelength, okay? And these are the parameters. The substrate was 8 mils, okay? And then I said, okay, well, what's the highest impedance I could synthesize with this line? Because you need that for the bias drain lines. So it turns out that 7 mils is the smallest that you can synthesized, which is that's 92 mil length at 20 gigahertz. Of course, the design is at 20 gigahertz. So, assuming that you have this file in here, which you're going to scoop into your ADS, okay? And that's this file in here, as you can see here. I read it from my local directory, and I assigned to it, I said, go ahead and calculate mu and the stability factor. And what I did is I did this and found out that the device becomes unstable below 14 gigahertz. So that means I want to go ahead and add stability to it, add stability components to it, okay? And that's, let's look at the second file in here, which I did. No, I didn't. Okay, so what is that? Let's see. This is, okay. This is basically in here. What I did is I added the stability circles. Okay, and let me explain just briefly how, okay, well, before that, the stability conditions, okay, we define the K and mu, the mu, and then the delta in here, the determinant of the S parameters. And you can refer back to Gonzalez's book, how he derived this. But basically, these are all based, these are stability factors that are based on the small signal parameters, okay, the magnitudes of these. Okay, and you can get that right here, okay? Now, so basically, you put these in here, you put these functions from the ADS, and you get this, okay? And you, of course, we realize that we do need to stabilize this. Okay, and here is my an example of my stabilization circuit in here. And to understand this, first of all, you really need to be well aware of the theory of amplifier design. Okay, and basically what it is. So we go into the device in here, and we added these components. I added these components, and basically what they do is, let me see. Why did we go into okay. All right. Well, let's go further. Let me postpone the stability circles a minute. So we added these here, and what these do is basically rotate the load of this device, the S parameters of this device, so that this device is stable. And let's run it. And of course, where is the K factor? So here's the K factor in here. As you can see, at 2 gigahertz, it's above 1. Okay, and it's above 1 at all of the frequencies. Okay, and of course, when you do that, of course, the price you pay is really your gain goes a little bit down. Okay, and of course, in this case, look at the S22. It has changed from what it was prior to that. Now, one thing I did is this network in here, this stability network, what it is basically, I've got this pole in here, okay, and then in here, I had a quarter wave line that is 90 degree at 20 gigahertz, which means at 20 gigahertz, because it's short, this will be open, meaning this resistor is not present. And I do that is because I want this equivalent, or the total impedance presented by these on the drain to be open or not to be present at the frequencies above in this region in here, and particularly in this region here, because that's what I'm going to operate at. I want it to be present in here so that it brings this stability factor more than 1. Okay, so I do that, and then of course the K and the mu becomes more than 1, which is desirable. And as you can see that the gain got reduced a little bit. So let me go back and show you what the gain, for instance, in here, the gain is about 11.87 at 21.2 and 10.9 at 17 gigahertz, where after stability, after you add the stability circuit, it becomes, let's see, what is it right here? You get 10.57 and 9.9 dB something. Okay, so it got reduced. But the good news is that NF min has not changed, which is right here. across the band, it's between 0.68 to 0.72, which is what we want. And that's why the stability factor, the stabilizing circuit was added at the output of the transistor. Okay, so now let's introduce stability factor. Stability factor, what circles, what they are, when you get the transistor, okay, you can plot the impedances. So this is the Smith chart, basically. Okay, this is Smith chart. So what we want is a stability factor is that, and we're going to assume that the S22 and S11 are less than 1, the magnitude. And that's valid because by inspection of the file in here, you look at the S11, this is all in here, it's all below 1. And S22, which is in this case right here, they're all less than 1, okay? And of course, S21 is very small, at least 1/10 of these values. And you can see that right here, the magnitude. S21, of course, that's the gain in here. And you can see it's about 4. And of course, 10 log of 4 or 20 log of 4 is around 12 dB. And that's really, that's why data sheets like this small signal model, by this, the minute you glance at this, you can see that how they assess the design of this device or how good this device is going to be, because you can tell how much is this small signal gain and and the isolation, for instance, which depends on S22 here, or S21, okay, and so forth. So and then it tells you the stability, how close this to 1, this and the S22. Okay, so basically we want these circles, and I'm not going to spend too much time on this, but what happened is that there will be some circles that we can draw for both the load and the source, where these circles will tell you where the regions that are stable, that because we got this transistor, and this transistor can have, depending on the frequency, the output impedance, the load impedance, and the source impedance are going to vary all over the place, because you want to make sure it's stable, regardless, go from short or open. That's what we do. We get this LNA after we design it, we put it on the bench, we power it, DC bias, and then we take the input off, we make the input off, unplug the input feed, okay, make it open, and watch if it's stable, watch if there is any oscillations from the lowest frequency to the highest frequency. Same thing we do at the output, and then we repeat it for short and for a combination of short and open. And then we can vary the supply voltage as well to see whether that it's really stabilized all over the frequencies. So in this case, because most of the LNA devices that we utilize, they're really the S11 magnitude and S22 magnitude is always less than 1. Okay, even though in the Gonzalez book he treats the S22, S11 when it's more than 1, but that's really probably power amplifiers or some other devices that are intended for other uses, because for an oscillator you do want these to be more than 1 at the input. So this circle, we draw it for both the load and for the source, and it's always, we want to make sure that this circle, the center of this circle, is outside the whole Smith chart, is because as soon as it touches the Smith chart, the areas that are the intersection area between the stability circle and the Smith chart is always going to be the place where the load, where the transistor will oscillate. For instance, for this particular case, we see that if your load is inductive in this quarter here at these angles, which is around from say about 20 degrees to like 35 degrees, and it's inductive, it's going to oscillate. Okay, and that could happen. That could easily happen at some frequencies. So we really want these to be completely out, and you can please refer to this book so you can see. So let's watch what happened when we basically take out these devices, deactivate these stabilizing devices, what will happen is as soon as we look at this, we're going to get of course, the K and the mu stabilities are going to be less than one below these frequencies. So if we check it at 2 gigahertz, we can see that at 2 gigahertz, this is the load, this is the stability, the load stability circle, but it's drawn with a little points crossing here, so it's going outside the Smith chart, and then the source is right here. We can see that this device that I have picked, which is this device here, we could see that most of the threat for oscillation comes from the load and not from the source. On the source is just a tiny area where it could be on this angle here that it's inductive, if you show inductive, okay? But the most terrible one is the load side is what could oscillate. So as soon, of course, this is showing it for this is showing you for the entire band from 2 to 24, and you can see these circles that correspond to or parts of a circle that corresponds to the load and to the source that are spanning from 2 gigahertz to 24 gigahertz. And you can see that these circles, and this is the gamma 1 is from right here is the impedance that is stable, the Smith chart, where the S11 is less than 1. As you can see that in these regions in here, always the circle will be intersecting the Smith chart. But as soon as you go above where the marker M6 is sitting at 14 gigahertz and above, you can see that they start departing outside of the Smith chart, just like we see in this case. Let's see. Okay, so we put those back in, and that's what we see right now. You can see that at 2 gigahertz, after you put the stabilizing components, that the source stability circle instability region is outside the Smith chart, and then the load as well. Okay, so which means that this amplifier can have any input and output impedance termination, and it will not oscillate. Okay. All right, so let's see. So now what we want to do next is then let me go back to here. So basically, just to show you to be live on this. So what we did is we came in here and we deactivated this. Okay, and so we let's run this, and of course we're gonna get the stability region is only this region, okay? This region here. The rest of this is all intersected. And of course, you can see that indicated as well in the K factor, which is below 1 for this, okay? And of course, these circles in here, now let's see what happened on the next one. As soon as I put back the stability portion of this and run it again, now, oops, no, below, well, they're outside. They're right here and one right here, but we're not yet going in here. Let's go back to, okay, let's go and inactivate these ones. Okay, so let's run it again, and we can see that, watch what happened. Okay, see, now all the circles are outside, where if I come back and deactivate these like this and run it, you can see that the circles has intersected the. Now, one thing we could do is just to show you. Let's see how much this changes. So I'm going to put the history of this on, and go back and run this again. Oh, no, I wanna. Okay, I wanna. Okay, do this and then run them again, and you can see now how it changed. You can see that the gain has dropped. Okay, you can see that dropped, and most of the drop at low frequencies. So at the higher frequencies of the region where I'm interested in, which is 17 to 21, it didn't drop as much. But you can see that S22, look what happened. And this is the pole that is because of the quarter wave shorted section. You can see that a combination of components that are on there had made a null at this frequency in here. So you can see that it went from this value to this value that is here, okay? All right, so let's continue. So now, then, once we're happy with this, okay, so what we're going to do next is basically okay, so what we're going to do next is we're going to go into the matching of this device. So let's take a break and I'll get back with you guys in a minute. Okay, okay, so let's go now. So what we did is we basically took a device that was unstable in some regions of the frequency and we stabilized it. So, but let me go back. There's one thing that I forgot to mention in here, and that is because we're designing this LNA amplifier based on using this device that we selected here, which is the CE3520. And I'm using the small signal parameters that are provided by the manufacturer to design this. Now, I said that as an alternative to this, you could also obtain the nonlinear large signal model from one of the model providers, but you have to pay for it from Modalytics in this case. And so now the good thing about this is that I can, this here, the design that I designed this using the small signal parameters, they're really at specific frequencies. Okay, they're specified at a specific frequencies because of each time you change the bias, the S parameters will change. And of course, at the beginning, we said that we wanted, let me go back. We wanted, the other thing that I wanted to also show you is that, for instance, I can design this LNA using this discrete device, so 3 stages, based on the small signal parameter, and I can assure that the gain and the noise figure is okay. I fulfill these, but really can't have any information on the nonlinear behavior of the device. For instance, like the OP 1 dB, the output 1 dB compression point, at what point we wanted here in this case, for instance, to have saturation power of 13 dBm. Now, coincidentally, so to do that, really, you need to use the nonlinear model. You need to obtain the nonlinear model from Modalytics or Keysight if they have one, or build your own SPICE model so that you can verify things like these. But the good thing is that, so I don't have access to this, I have access to small signal, is that right here, look, power output dBm, okay? Which means that this device is really capable of giving you this much power. So that shows me that if it saturates at 14 dBm, then for sure the P1 dB will be greater than the this value here. Okay, so it's very similar to this. That's another thing. But if you get the nonlinear model, that's nice because the first thing you want to do is run the device alone at the specific bias voltages that you want and verify that the S parameters that are provided by the manufacturer, that's the way really to sync your nonlinear model with your small signal model, is to obtain the S parameters from the manufacturer at a specific bias point. Like in this case, for instance, it's 2 volts on the drain and minus 0.4 volts on the 10 milliamps on the drain. Is that you can run your nonlinear model at those points and compare your S parameters with these. And you should be able to correlate. If you don't, then obviously this model is no good. And I believe Modalytics has published a lot of these informations and verified that yes, our models really match these ones here. And then you can actually, in that case, you can sweep this device at the input power level and find out where it compresses, what saturation power point, what's the third order intermod value is at specific input, and so on. But for right now, I'm assured that this device will fulfill the needs that I want because it is right here. It's mentioned that it's done this. Okay. So let's go back now. So we did stabilize. We computed the stability factors, and we ran that, and we said that the device is unstable below 14 gigahertz. So we added a stability section that will show up mostly at the frequencies below 14 gigahertz, and that's when we recomputed the stability factor, and it's fulfilled that it is unconditionally stable right now with those circuits. Now, of course, we drew the stability circles both for the input, for the load, and for the source, and showed that with the stability factors, without them, yes, we do have an issue with the load mostly, and with some areas at 2 gigahertz. From 2 gigahertz to 14 gigahertz, the device will have instability circles that intersect the Smith chart, which after we have added the stability circuitry on the load side, boom, that's the Smith chart is clean. We can only see the edge of the load and the edge of the source. So which means this amplifier can be presented with any impedances at the input and output and not oscillate. Okay. So, and we did show that right now after the stability factor, and this circle in here is the Smith chart, the normal Smith chart with S11 less than 1. We showed that from 2 to 24, we swept the frequency and looked at the circles for every specific frequency in this band at 1 gigahertz spacing, and we can see that both the load and source are all outside of the Smith chart. So it's unconditionally stable. So next thing what we want to do is put back the stability circle in circuits in there, and then what we're going to do is we're going to put these two calculators in here in ADS. So we're going to go to ADS, and we're going to go to the schematics and add these. Well, we added these stability circles in here, so we did compute that. We found that we're done with that. Next thing we want to do is we want to draw gain circles and noise figure circles. So we added this from the, and you can add that in here. They're right here, basically. They're right here. These palettes in here, you can choose from these and get these. So I'm gonna draw the noise figure circles that corresponds to NF min, and then these values in here from 1 dB to 0.5 dB. Okay, I'm going to add these circles, and I'm going to add, I'm going to plot the gain circles that correspond from 9 dB all the way to the maximum gain available from the device. And when we do that, of course, we're going to get these circles. And of course, what I did also is I added the load stability circle and the source stability factor circles in there. So here is my this is my Smith chart, but this Smith chart, I made the scale is a little bit larger, so I can show the stability circles that are there, which is this and this one, which is for the source and load stabilities, which are outside this here. This is where from the zero impedance point, short load emitter. I could go back and just simply make this one and only look at the normal Smith chart. But in here, notice what happened. So I'm plotting these ones in here. I'm plotting the gain circles and the noise figure circles. And please correspond to Gonzalez's book. I'm assuming here that you have the background in microwave transistor design, amplifier design. So I'm plotting these points, circles in here, And what it does, I also plotted as well on here, is the conjugate of S11, okay? Because in the normal, for a power transistor, for instance, the conjugate of S11, which is right here, this here, okay? M4, okay? And M4, if you look at M4, it's this impedance is in here, which is 32 minus J42 at 20 gig. I'm designing the whole amplifier at 20 gig, okay? So in a normal case, you would want your transistor be presented with with this point here, okay? But this is not a power transistor. This is really a low noise amplifier. So what I want to do here is look at the noise figure circles, which are the blue ones in here. So here is one, here's another one, a third one, and a fourth one. And they vary from basically the noise figure minimum, which is just a dot right here, the dot, and M7 and M1. Okay, it's one of these. I'll show you in a minute. And then you go out to these values in here. So until you get the largest one is M6, and M6 in here, if you look at the markers, it corresponds to a noise figure of 0.6. No, sorry, it's one right here. It's one. Okay, all right. So now what I want to do is I want to do a noise figure source matching. And the way to do that is I want to see this point in here, which is, and of course, let's go back to the gain circles. The gain circles are the red ones. And they start from a dot in here corresponding to the maximum gain. And the maximum gain in this case, it is shown here. It's 11.8 dB at 20 gigahertz. All the way down, reduced by these fractions of a dB. Okay, in particular, I'm plotting 11.3, and 11.3 is really this circle in here, this one here. Okay, this circle here. The reason I drew this by trial and error is because I wanted to intersect the Fmin. Okay, so which means now I could choose this point to do my source matching, and that will allow me to have 11.3 dB and a noise figure of what's shown on M1 and 7. Let's see, a noise figure of basically okay, so the gain will be 11.3 at M7, and the M1, okay, the noise figure is on this side, is 0.6 dB. Okay, and that's really what I'm going to do. So, and so I did that, and so basically what we want to do, we want to make this load look like to the device, put a matching section in here that will make the impedance look like this impedance in here at M7 or M1. And M7 and M1, the impedance is, as you can see, is 30 ohm minus J27, or 29 minus J28. Okay, so, and that's what we're going to do next. Of course, now what I did, and now notice one thing, by the way. Notice that this point in here, M7 and M1, corresponds also, if you look at the gamma at these points, this point in here is 0.414 with an angle of minus 106. And guess what? That's exactly what the manufacturer said. If you want to have 0.58 dB of noise Fmin, then that's when your gamma magnitude is 0.415 and minus 106 degrees. Now this text in here needs to move over to this so that the angle is right here, the magnitude is right here. Okay, so that's another way of checking. So now next what I'm going to do then is, okay, and this is, I did this exactly the same. I just drew this list circles so to show you that the 0.69 dB of noise figure at this impedance level right here will intersect the point at 11.3 gain with 30 minus J27 or 28 or 29. You know, we're not trying to be 100% accurate in here because it'll give you by fractions of a dB. So, and to do that, okay, so let's check if that's true. So we're gonna take okay, well, all right, so I'm going to come back to this here. So let's go ahead and go to the source. So go to the device. And what we're going to do now, the other thing that I forgot to mention, let's go back. There is one which is the output matching section. The S22, I drew the S22 in here, and basically it is right here. That's the conjugate of S22. This point right here at 20 gigahertz. So what I'm going to do also is that the load impedance has to match. I will have to transform the load from this point to the 50 ohm in here. Okay? And that's basically my impedance at that point is right here. The conjugate of S22 at 20 gigahertz is 34 ohm plus J5. And you can see that the inductive part is tiny. So in fact, you add a little tiny capacitor and you can bring that in here, and then you still have to transform it back to this point here. Okay, so now I have the optimal load impedance and I have the optimal noise figure impedance, which is this point here. Let's check if really we can get that. And the way to do that is you come into your amplifier. I'm going to deactivate the 50 ohm load and the 50 ohm source impedance and present, I'm going to change the 50 ohm in here to the impedance that gives me the gamma for the minimum noise figure, which is at this gamma here. Okay. And I'm going to put the load as well at this, and I'm going to run it as an amplifier. So what that will do, that will really check if this amplifier, if this transistor now will give you the desired behavior that you want, which is I want a noise figure of 0.6 dB. I want the gain to be somewhere 11.3 dB. And let's do that. So I presented a signal generator with the same impedance as required by the gamma opt, and a load impedance that is presented by the S22, the conjugate of S22. And voila, boom, look at this. So here is my frequency response from 16 gigahertz to 24 gigahertz. And look how nice this is. I got my gain behaves from 10.26 to 11.28 dB. The gain is right here. And the S22, S11, and S22 are right here. You can see that S22 is really great, nice, very nice. Okay, the very large, very small refraction factor, 25 dB and 60 dB. But the S11 is not so great, but it's acceptable for me. Okay, it is between minus 11 to minus 8 dB. And the reason for this is because I really did not match this transistor for minimum reflection loss. I matched it for, as you can see, let's go back to the Smith chart that shows, okay, this one, okay, this one right here. Okay, I showed on this one, I showed the conjugate of S11 is right here, this point here. Okay, and then I showed also the noise figure, minimum noise figure, which is right here. And they're not the same. If I wanted to match for the conjugate of S11, the best value at 20 gigahertz, I would have to match for this value, which is 32 minus J42. But that's not going to give me the minimum. That's going to be on this circle right here. And let's go back and find out what is the noise figure of this circle. That's the second one. And the second one is 0.8 dB. Okay. Well, all right. So let's go back to, okay. All right. So if you look at this now, this is S11 right here. If I want to use this circle right here, this circle corresponds to, okay, let's see which one is this. I'm going to put a marker on this circle in here to see which noise figure that is. That's M2. So M2 that's 0.8 dB of noise figure, and that's not really what I want. So that's why when you look at the design of the when we designed this circuit, when we matched it, let's go back to the one where we replaced this one here, where we replaced the source with this impedance. This impedance corresponds to this point here, not this point. So when you run this, okay, of course the load is corresponding to S22 conjugate at 20 gigahertz. When we run this, okay, notice that S11, which is right here, let me thicken this so we can see it better, is not going to be as great as S22. S22 was designed, the match here was designed with consideration that the S22 reflection coefficient is minimal. But in here, we wanted to design this so that we can have the best noise figure, and there it is. Now this shows the minimum. This is the minimum Fmin specified by the manufacturer. Okay, and above that, the ball right here shows the noise figure obtained, and it's anywhere between 0.7 to 0.8. And in here, it's got deteriorated a little bit. That's because the stabilizing circuit impact on the lower frequency section, okay? And it did reflect back on the input, but it's still acceptable and nice, okay? So now I have done this. I have verified that what I need to do now is I need to match this circuit in here, so transform the impedance level from that is presented from 50 ohm to some kind of impedance here that will be this value in here. Okay, same thing on the input side as well. Okay, so let's go ahead and look at that. And to do that, I'm going to resort back to basically the Smith chart matching. Okay, so I'm going to go to Smith chart matching. It's a tool in ADS, but let's just look back in here. So on the Smith chart manually. So we know that what we want to do is transform. This is the noise figure circle that is tiny in here. I want to go from here to the load. So what you could do, of course, we can't use lumped components. If we could use lumped components, I would go with a series capacitor from the 50 ohm in here. I would go with an inductor, for instance, and then a capacitor in shunt, and then a capacitor in series, and I would arrive at this point. Your typical matching techniques. But what we have to do in our case, we really have to do it with transmission lines. So let's do that right here. So what we're going to run this tool and come in and put the impedance in here at the source and put the load as being 50. And of course, this point here really corresponds to what? Yes, it's the gamma opt, which is the value that is given by the manufacturer. Here it is. The magnitude is 0.4 and minus 106. And also given by the simulation that we did, okay, which is right here, which corresponds to this point. So we're gonna put that on the Smith chart, and then what we're gonna do is we're gonna use the series and parallel open stub to do the matching to arrive at 50 ohm. I don't want to use short stubs because otherwise you're gonna have to use vias to go to the ground, and it's too risky. Even open stub is going to have an open end effect, fringing effect, but that's okay. It's still better to fabricate with this than this. And another reason also is because I really I'm going to have the DC supply present at this input matching network, and in that case, I don't want it to be short. I want it to be open. So the first thing we want to do is really we want to go from here to here, okay? So one thing to do is you can go from the source to here is by simply putting an open
stop, that will drop you down here on a parallel. I'm not showing the other the Y circles, the Y plane. So that will give you here, but really it's going to end up being somewhere around here. It's not going to, you still have to go with a serious line to get to here, okay? And that's what I did here is I went with a stop, open stop, and I got to here and I said, this is good enough, really. I don't want to add another component because at the input side, I want to stay with minimal copper work because that will minimize the losses and preserve the noise figure. So this shows you the here. And then in that case, of course, the circuit is really like this, okay, the input match circuit. This is just 0 ohm, it's not showing. And I run the simulation and you can see that I did achieve the required noise figure. And the S11, you could see that it's tuned. It has this, but the S22 is not yet activated because I have it right now. It's not present, okay? So let's see that on the this here. So so this is okay. This is the Smith chart, okay? Now right now this was designed early, so what you see is this. This is the equivalent circuit of what's in it, okay? The same thing now on this one here, I designed with the same technique, and this is what you end up with. There's a little series one, okay, and a shunt one, okay? And so I did not use any optimization. So if you run this, you will get basically, here's what we got as a frequency response. The noise figure is between 0.8 and 0.75. The gains are between 11 to 10.8 to 10, okay, which is very nice, okay? Now, S22 is very good, and S11 is okay, minus 11 to minus 5 dB, which is okay for right now, all right? So that's this. Now, next, let's get rid of this and let's present. By the way, the way you get this is you get it from the tool. So basically what you have tools in here and you have a Smith chart in here. This is basically what you get it. Okay. And this is right now is looking at match 1, okay, which is this one here. Okay. And so you can see that you can vary all this. And once you're done, I basically come in here and go next. Here is where I deactivated these and I brought out these ideal transmission lines that corresponds to the actual match, and I run this, and this should give me the desired response, which is nice and neat, between 17.2 to 19.2, which you can see it's beautiful. Both the noise figure is fulfilled, the return loss is fulfilled, everything is fine. So right now, what I got is this. Now, of course, my load impedance is at 50. At any time, if these misbehave, then I can resort back and put the actual impedances that it has to present, which are right here at the load and source. So having done this, guess what? The next thing I want to do is copy this 3 times, okay? Right? We're going to copy it 1 time here, another time here, and another time in here, and run it and see what we get. Ta-da! So basically, here's your 3-stage amplifier. The gain in here is between 32.6 dBs, 32.6 and 29.8, which is nice and neat. Okay, S11 is shown right here, which is pretty good, very good. Okay, and then the noise figure, the overall noise figure is excellent. Okay, so let's add one more marker in the middle just to show you. Okay, so which you can see here from 0.8 to 0.75. Of course, somebody might look at, and of course, on the Smith chart, I showed the S22 and S11. And you can see the S11, the impact of the fact that we're not really designing for optimal minimal reflection loss. We're matching with noise figure matching, okay? All right, let's save this. Now, of course, what do we do next? So we have this now. These are transmission lines. These are basically basically these are right now ideal, right? So what we need to do, we need to put back real copper in here. And that's what we're going to do next is, as you notice, of course, I did not do any optimization to this. Okay. We have not done any optimization. And the reason is because of this is I wanted to design it in ideal case right now with ideal everything. Even the cab is here is ideal. The resistor is ideal. But what we're going to do next is pick components, these are passive components. And the other thing that I wanted to also show is that we need to block the DC in here. We need DC caps, decoupled caps that will behave good at 20 gigahertz or 21 gigahertz. Same thing, we need these packages, and we need to put real copper with the substrate properties in here and put the other discontinuities and run it again. And that's where we're going to end up with issues from parasitics and so on that we have to use optimization. Okay. So as an intermediate stage, what I did is the next thing I did is I said, let's go and for instance, let me pick some, let's see, what is this doing? Okay, here it is. All right. Oops. Okay, I lost it. Okay. All right. So that's what we're going to do next. We'll postpone that to this time, next time. So I want to go back to one thing that I had. Now, you see all of this business doing the stability factor, stabilizing, plotting stability circles, and then gain and noise figure circles. With all of this, you can actually do with a template, okay? And the template that is available from ADS, from Keysight, I did not want to use it, to be honest with you. I hate templates because they're automated and there's so much in the background that it doesn't make me feel comfortable and doesn't make me feel in peace with myself that this is really what I'm getting. So I needed to do it myself. But you can go ahead and go to get the device and put your stability factors, and then into a template. And the template, you can run it and it will give you all of this. And it's automated with moving markers that you could move around at various frequencies. And it does give you, for instance, in this case, this template gives you matching for gain or matching for noise figure. Okay. And it gives you everything. It gives you the noise figure, gives you the stability factors, gives you the K factors, gives you the gain and an optimal source and load impedances and so on. So let me show you how that is done. So what I'm going to do, so here is my circuit. I got this template from ADS. Okay. So, and what I'm going to do is I'm going to run this. So I'm going to run this simulate. And right now I don't have anything, but what I'm going to do, I could go in and start plotting, of course, let's say I want to do my, I want to get my S parameters, for instance, all of them. Okay. Oh. I want to get, for instance, these guys in here, add them in dBs, and then start looking at this. But I don't want to do this. I want to insert the template that gives me all of these calculations. So you go to insert and you go to template, and you can get these templates by Keysight. And what they are, they're live templates because they have a marker in here where you can move it. Okay, and I'm going to move it to 20 gigahertz to see what I get. Okay, and right away, I got all the calculations, and look what happened. I really got the same exact thing. So here's NFmin. Okay, here it is, and here's what the Z-opt has to be at the input side, and here's what the Z-opt has to be at the output side. And here's the gain that I'm going to get, which was 11.3 dB. Remember that number? Where if you had to design this for matching for gain to get maximum gain, you would, of course, your values would be different at their source and load. And then your gain will be much higher. In this case, 11.7 instead of 11.3. Okay. And of course, you still got exactly the same loci on these points. Okay. So that's what we get. All right. So what we have, ladies and gentlemen, is we have designed this low noise amplifier, and it's 3 stages, and here they are. And here's the response. It's beautiful, nice. So right now, next thing I want to do is basically finish this design in here, where I have to add the bias circuitry, which involves microstrip work, because you have to use quarter wave lines, you have to use radial stops, and so on. And you have to verify that the drain and gate microwave circuitry and lumped component circuitry did not deteriorate the gain of the overall amplifier. Also, you have to change these ideal lines now to actual substrate-based microstrip lines and add all the discontinuities that you want to add on there. And then run optimization, tweak it, and when you're happy with it, you're ready to transform this to your schematics, okay? Now, it's up to you by then. Some people, what they do is they get completely this done and they send it to the schematic people, or they could do like I did previously on one job that I did several years ago, which I showed you earlier, where this is cadence in here showing, I drew the schematics in here. All of these components are basically passive components that are available in the cadence library, or I brought the footprints and so on. And then I have the device, which has a footprint. And then what I did is I made a block in here, a 3-terminal block and a 3-terminal block in here. And these actually had in it everything that encompasses this, which is basically the input and output matching along with the other things in there as well. All of this. Okay. So you could do it that way. It's up to you then, how much work you want to transfer over to the some people, they come out of ADS complete with a complete Gerber file, but I'm not going to do that. It's just too different, because I've got other things in the LMB. I've got the power supply, I've got the local oscillator, I've got the reference 10 megahertz reference distribution signal, and amplification and filtering. Okay, so the next thing that has to be done once that is done is to go into the waveguide to microstrip transition. And that's basically, let me borrow, this is posted on the net. So this really shows a K-band LMB in the old technology, which doesn't have phase lock loop. This has a DRO oscillator in here. But you can see here's one waveguide aperture in here where this is I'm almost certain that it's the same device that I'm using. You can see the probe going into the aperture, okay, into the waveguide front. And you can see here that on the input side, this is the negative bias, and they used, in this case, open stops to do and a quarter wavelength, of course, very high impedance in here, probably 100 ohm. You can see them, the thin lines in here. But the open stops are low impedance stops. And then, of course, you go into the device, and then the output, they use this. They didn't really use capacitors, passive components. They use just basically like implementation of a capacitor or a quarter wave line, coupled line in there. And then they go into a second device in here, and then filter, and then a third device, which is now this device is different than this, because usually this device is much more expensive than this because of its noise figure. So in this case, they have this device, filter, this device, and then the same device in here, they use it as a mixer. Here's the LO, they split the LO into 2 ports, suction with a Watson divider in here, and then they mixed here, and they went in, and of course, into the in here combined both the vertical and horizontal, or vice versa, and then went into the IF amplifier in here, and that IF amplifier, here's the F connector in here that gives you the IF. So this is what we're going to do. This part in here, which is very critical, is the actual design that is here that you can see in here. So we're going to have to do this, and the reason I want to finish this is because I want to go back to my three-stage amplifier. I want to go back to my amplifier in here and then replace the 50 ohm in here with this, with the S parameter that are exported from here. Okay, so what I'm going to do, I'm going to take from here, I'm going to take the S22 of this thing in here. This is S11. Let me see. Let me get S22. Oh. Okay, so I'm going to get the S22, which I'm going to get right here. And okay, so I'm going to take the impedance that is presented by the by the microstrip to waveguide transition at this point here, and this feed line is a little long now because so what we need to do, we need to reduce the length of this. So let me just make sure I grab the right thing. Okay, the copper. So that's the probe, the feed. Okay, that's this line in here. The length of this L feed. Okay, so what I'm going to do is L feed, I'm going to reduce the length of this. So L feed, say 20 mils. Okay, so what I'm going to do is get the impedance that is at this point, okay, and then go on to the LNA. I'm going to take this, export this to ADS, and now I want to have my three-stage amplifier in here driven by the impedance that is going to see, not 50 ohm, but what it's going to see at that point from the microstrip to, and that impedance is right here, basically shown in this response in here. Okay, ladies and gentlemen. So basically, this really covers the part 5 of this. This is Dr. Mohammed Nizami again. I thank you very much. You can get in contact with me if you'd like on this phone number. I operate of Jerash, Jordan. And right now I have some bandwidth for, I'm involved in 2 projects, but I still have room for a 3rd project. If some of you have any design work that you require to offload to offshore design service, please get in touch with me. Thank you very much and have a great day, ladies and gentlemen.